Okay, this is day two of linear regression, which is residuals and reading computer output. So we're going to kind of take it the next step in linear regression, kind of talk about some of the different parts to it. All right, so the first thing is the definition of what is a residual, right? So a residual is the vertical distance between a data point and the regression line. So if you look on this picture over here, this line right here is the regression line that's going through here. So this is your least squared regression line. So this is the one, you plot the scatter plot, and then you're going to do the line of best fit or the least squared regression line, put it through your data. And then these little dots that they have here, right, these are your actual data points that you have. Okay, so you have, some above and then you have some below. So this is actual data that came from, what you use to make your scatter plot. So then what happens is you write your equation, right? So, last time we talked about this. This is our least squared regression line, right? Where we have the slope, the y-intercept plus the slope times x. So what happens is once you start putting in all these x's, you're going to get out a predicted y. So this right here, all this on this line right here, this is made up of a whole bunch of y hats. There's just a ton of y hats all along this line right here. Okay, so then what is a residual? The residual is going to be the distance between the least squared regression line, which is made up of all the y hats, and the data points. So it's going to be what they said was it's the vertical distance. So it's actually going to look like this. This is your vertical distance right here. So this is your residual. Okay, so how do you look at a residual plot? This is a scatter plot down here. Just, what we've done before. So we made up a scatter plot. This right here is our residual plot. Okay, so what they've done is if you look at this, this is our least squared regression line. They've basically flattened out the regression line, and now you can see it. So this part right here stays the same. Okay, so this is still your x values right here. Those don't change. But what does change is instead of having the y's this way, this is now your residual. So this is going to be your vertical distance of how far each data point is from the regression line. So this is going to be a residual graph. So remember that we talked about the formula for residual, right? The formula for residual is going to be equal to y minus y hat. So remember that this one right here, this is our actual data point, and then this is our predicted data point. So it's going to be our actual minus our predicted. Okay, so there are basically three different types of residual graphs that we normally see. And it says that the residual plot is used to determine if a line is a good representation of the data set. So the whole purpose of doing a residual plot is so that maybe you can get a better picture than what you would get with just a regular scatter plot. So sometimes you look at a scatter plot and you think, oh, my data set is pretty linear. But then when you look at the residual plot, you can see, oh, no, it's not linear. It was probably more quadratic or more exponential. So we have three main graphs that we're going to look at with the residual plot. So this one right here, this first one, we'll call this, graph number 1 right here. This one is, you can tell that, see, it's just like random all over the place. So really, when you're doing your line of best fit, what you want is you want it to go through the middle of your data. You would like for it to be evenly dispersed on the top and the bottom. So you can see that you have, a lot of data up here on the top, and then you're going to have a lot of data here on the bottom. And so with this graph here, see, they put in red that this is our least squared regression line, right? As we said from the last slide, this is our least squared regression line because it's flattened out. And then we describe this as random scatter is what we say. So it's the residual shows random scatter, and so a linear model is appropriate, right? We say yay for this one. This is good. This is a good linear model. We think that we have a good scatter plot, good least squared regression line. Okay, so then this one over here is going to be, this middle one is going to be graph number 2. Okay, so for graph number 2, you can kind of see, that it's going to have a pattern to where it's fanning out, right? So it's kind of like this cone. You can see that they've put the lines down here on this bottom graph in purple, right? They have the line here, and have the line here just to kind of show you how it fans out. So what this means is that it's forming some sort of a pattern, okay? So for this one, we say that the residual shows a fanned pattern. A linear model is not appropriate, right? There should be some other model that would go with this. We don't know exactly which one, and we don't necessarily have to name which one it is. We just have to say whether or not a linear model is good, So this one gets kind of the sad face because this one is not a linear model. So if you were to see this residual graph, you would say, this residual graph shows a fanned pattern or some sort of pattern, therefore a linear model is probably not appropriate. Okay, so then the last one that we normally see is graph number 3. With this, you can see that, it's doing some sort of a pattern like this where it's coming up and down. You might be familiar with this from like Algebra 2, the quadratic, right? We've got this upside down parabola. So you can just see down here that, the red is where our least squared regression model would go, but obviously it's not linear at all. It's more of a quadratic tone to it. So again, you don't have to say, that it would be a quadratic. We can just use this word that it is a curved pattern. Therefore, a linear model is, again, not appropriate on that one. So this one, or I'm going to put so this one is another sad face. Yeah. So again, just to kind of recap on this, number 1 is a linear model is appropriate because it shows random scatter. Number 2 is it does not show, or it's not a linear model, or it's not appropriate, sorry, because it shows a fanned pattern. And then the last one is it's a linear model is not appropriate, again, because it shows a curved pattern. So those are kind of the 3 main graphs that you're going to see. Okay, so we have on the next one, we have outliers and influential points. So those are 2 things that you're going to see with linear regression. We've talked about outliers before when we were doing, exploratory data. We used them when we were talking about like our box plots and stuff like that. So an outlier is a data point that is far away from an overall pattern in the sample. Okay, so basically it's just like you've got all these data points here. Okay, so you see how they're all pretty close together, and then you've got this one that is far away from the rest of them. So this guy is sitting way out here at 25, and these are going from what we could say that this is probably maybe 3 or so. And then this may be 11 or 12, something like that. So these are in the range here from 3 to 12, and then you've got this guy way out here at 25. So this would be an outlier. It's just a point that is far away from the rest of the data. Okay, so on the other side of this is the influential point over here. Okay, so an influential point is an outlier. So this is an outlier, right? In the x direction that has a large effect on the slope of the regression line fitting the data. So here's kind of what happens with this one. So if you notice, right, we've got our data going here. This is our pattern. And again, if we drew a line down here, this is maybe 3. If we drew a line down here, we could be, again, at maybe 12. Okay. So then we've got, this guy that's sitting out here at 25. So this is far away from the data. So it does meet the outlier criteria. Now, what makes it different than the first picture over here is that if I remove this data point, right, if I put an X through it and it's no longer there, and I'm only looking at this particular pattern over here that's circled in green, if I decided that I'm going to fit a regression line through this, it's going to look something like, okay, let's see if we can draw it. I'll pretend I can draw straight, but something like that. That would be my new least squared regression line. Well, if I do that, then it definitely influences the slope of the regression line. This one, you notice, had a negative slope, right? It was going down. If I take this influential point out, now when I'm looking at this, if I'm going to put a regression model through it, now it's going to be positive. So and if you went back over to the first picture, if I removed this particular dot from it, okay, then this would not influence this line. This line would still go like this, right? It's still going, it would still go straight through this like this. It's not going to change whether or not I have this point or not. This one, definitely, if I take this out of the picture, then my line is going to change. So that's the difference between an influential point and an outlier. An influential point is an outlier, but it influences the slope. All right, so this is reading computer output. So with reading computer output, they use this a lot on the AP exam. One, they do it because it's an easy way for them to test whether or not you actually know the concept without having to type the stuff into your calculator. So why do they do that? A lot of times, one, the test is timed, right? So they don't want you to spend all this time typing these numbers into your calculator. And then 2, you can make mistakes. Sometimes with the calculator, right, you could type in 2.5 instead of 2.4. You could switch the numbers around, and so they really don't know if you don't know the concept or you just didn't do well when you were typing it in. So this is how the AP exam tests a lot of these concepts on linear regression. So we're going to start and kind of read through the problem. So it says the following output data from Minitab. So Minitab right here is a computer output program that they spit out all this information that's down below. So it shows the height of girls in centimeters based on the number of years old. So what it does is it spits it out into certain columns. So we'll look at the first column here, which it says predictor, right? And we'll talk about that. So under predictor, it says constant and then age. So with that, with the constant is your y-intercept. Okay, so back when we were talking about the least squared regression line, this is actually going to give you the value of the y-intercept. So the value of the y-intercept is 76.61. Okay, so then the next one, the age, this is going to be where your slope is going to come from. This is actually your x, right? And they put it in context of the problem. So if you notice, it said that it shows the height of girls based on the number of years old. So this right here is your slope. So that means that the slope in the problem is this 6.366. Okay, so the next column is our standard deviation. So when you're doing linear regression, we are doing linear regression for the slope. It's all about the slope. We don't care about the y-intercept. So that means that we don't care because this is my y-intercept column along, or row, I guess, the top one. And then my second row is all about the slope. So that means that we do not care about the standard deviation for the y-intercept. We don't care about the t ratio of the y-intercept, and we don't care about the p-value for the y-intercept. The only value that we care about with the y-intercept is this initial one, which tells us what the y-intercept is, which is 76.61. Okay, so down here on the slope, we know our slope is 6.366. We also know that the standard deviation of the slope is this 10.1672. Now, this gets what they call this, the value, it's SE with a little b down here. That's standard error or standard deviation of the slope. Our test statistic is this 38.0T. 38.02, not T. This is going to be our T value, right, equals is 38.02, which we get into a little bit later on in this course when we start to get to inference. And then this is our P value, which is 0.000. So this would be the P is equal to, right, this value right here. So we got T and we got P. And again, we'll talk about that a little bit later. All right, so the next row down here, they normally have these out to the side. So this is just plain S. So this is standard deviation of the line. So a lot of times people get this confused, okay, because this is standard deviation of the line, and then the one that was over here, this 10.1672, is standard deviation of the slope. So normally when they're just asking for standard deviation, they want this one, okay? If they're going to be very specific, if they want the other one, they will say, what is the standard error of the slope or standard deviation of the slope? Okay, so next we have our r squared. So we also said that the r squared, the name for it is the coefficient of determination. So that is going to be our r squared. Okay, so that's going to be 99.5%. Then we have over here, we have r squared adjusted. Okay, so this one is 98.7. We're going to always use just plain old r squared. We're not going to use the r squared adjusted. So do not use the r squared adjusted. So if you notice on this computer output, they don't give you r. So if I wanted the correlation, then I would have to just take the square root of the r squared. So I would take the square root of 0.995. And then whatever I would get, then I'm going to erase my little things right there. Whatever I would get, then I would go over here and I would have to decide if it was positive or negative, right? And how I would decide positive or negative would be based on the slope, right? So this piece right here, whether I'm positive or negative, is determined by the slope. Because this r squared is always going to be positive, right? Because anytime you square something, you're going to get something positive. But when I take the square root of it, I have to decide which one is it. Is it the positive or the negative? And I have to go back to this piece right here, my slope, and decide. That will help me determine whether it is positive or negative. Okay, so we're going to go through and we're going to try to fill in this chart based on the computer output that we have over here. So remember that from this, if we look at our computer output, this first row refers to our constant, right? So this right here is our y-intercept. Then if we go through and we look at the second row down here, which is age, this is referring to our slope. So that kind of like helps us out. When we are doing these regressions, we're doing it as far as the slope. We're not doing the y-intercept. So basically, you don't have to look at the top row, so we can kind of like eliminate this stuff right here when we're looking at computer output. Okay, so the first part says find the following, which is our slope. Okay, so the slope is B1. So if we go over here to our computer output, we go down to our second thing, which is our second row, which is the age, and then across from that is our slope, which is going to be this number right here. So it's going to be 6.366. Okay, so then if we find the y-intercept is going to be our constant, which is our first row right here. So the coefficient of our constant is this 76.61. So we're going to write 76.61. If we put it all together and we write the equation of the LSRL, which is our least squared regression line, that would be that we would take our y-intercept. So our dependent variable is going to be height, right? We are finding the height based on the age. So our age or our years is going to be our x variable, and then our height is going to be our y variable. So how we're going to write it is we're going to write it as our height, and then we're going to put a hat on top of it because that tells us that we're doing our predicted height. And then we write the y-intercept first, so we would put 76.61, and then we would put the slope, so plus, and then we would go back up here, which is 6.366, and then we're going to put our variables, so we're talking about age. So whenever you're doing it in statistics, you have to define the variables. If you're going to use the letters y and x, then you're going to have to tell them what those specific variables talk about. Okay, so our correlation coefficient, which is r, we're going to come over here and we're going to look at our computer output, and we notice that they do give us r squared. They also give us r squared adjusted. So r squared adjusted, we are not going to use r squared adjusted, we only use the r squared. Then if I'm trying to find the coefficient, the correlation coefficient, if I know r squared, then in order to find r, I'm going to have to take the square root of that number, so 0.995. So if I go to my calculator and I take the square root of that number, I'm going to get 0.997 as my answer, 0.997. Now, I do have to check to see if it's positive or negative, because remember, r squared is always going to be positive. So you have to go back and you have to look at the slope. So our slope was positive, right? It's positive 6.366. Therefore, the correlation is positive. So when I go over here, this is 0.997. Okay, so then you also have to do the coefficient of determination, which is r squared. So we said we're always going to use regular r squared, not r squared adjusted. So this you're going to write as a percentage. So we would put 99.5%. Our standard deviation of the line is just S, so you find S down here. On about the third row, it's kind of usually underneath all the regular information. This is standard deviation of the line. It's also standard deviation of the residuals. Okay, so this is going to be this 1.518. And then our standard deviation of the slope. And so remember that the second row has to do with slope. So we would go to the column that refers to standard deviation, and then we would drop down to the second row, and this would be standard deviation of the slope. So this would be 10.0 0.1672. All right, so it says to interpret the standard error in context of the problem for each data value is 1.51 units from the regression line. So this would be basically an interpretation of it. Instead of saying each data value, it should be this, on average. Each data value is 1.518 units from the regression line. And then we'll get into a little bit more as far as like the sentence stems as how you would write this on the next screen. Okay, so we talked a little bit about the standard error of the regression line, which was S. This is the standard deviation of the residuals. So S represents the average distance that the observed values fall from the regression line. How we're going to interpret that is, sometimes they're just going to ask you to find it. So you just have to look at the computer output and you're going to find what S was. Then sometimes they're going to ask you to actually do an interpretation of it. And so it's the average amount that the observed Y value, okay, and so the observed in our particular example, our Y would have been height, right? That the height values differ from the predicted values. And then we would put is, and then our S value was the 1.518, and then we would include whatever units that they were talking about in the problem. So the standard error of the slope is this SE with the little subscript of B. This is the standard error of the slope or standard deviation of the slope. This is the standard deviation of the slope, and it's that the data comes from only one sample. So this is the variation that you would get of your slope. So every time you do a different sample, you're going to get a different slope. So the interpretation for this one is if we gathered repeated samples, so if we went out and got, a bunch of different samples, then we're going to get different slopes that go with it. So we would expect the slope of, and it says the Y in context. So remember, for our particular example, that is going to be our height. Let me erase this really quick. So this right down here, this would be our height because that is our Y variable. So we would expect the slope of the heights to vary by approximately, and then we had as our standard error, it was this 10.1672, and then whatever the units were on that one.